Now let's discuss the types of indexes and how they work. Oracle uses a number of types of indexes and a number of other types of database objects which could be classified as indexes. The most commonly used index is the B-tree, or binary tree. By binary, it implies each item within a tree has two separate options. This is not essentially 100% true, but that's the idea. A binary tree is really a tree-like structure upside down where one option leads to multiple options below it. What's a bitmap? A bitmap is literally a map of bits. If you took a square, a two-dimensional square, and you cut it up into blocks, you'd have zeros in some blocks and ones in other blocks. Really, that's what it is. It's a two-dimensional picture of ones and zeros. Function-based index. A function-based index is an index made from a function. In other words, you apply a function to a variable value, as in a column in a table, and the result of the function becomes the index. An index-organized table. This is one of those things that I was talking about as not necessarily being an index, but an object. It's actually a table as well. As we discussed previously, an indexed-organized table is really a table with its data physically organized and sorted by the index. A cluster is similar to an index-organized table. There are two differences. Firstly, a cluster can be made up of a join, that is more than one table. Also, the cluster does not necessarily contain all the columns from the tables in the join. A bitmap join. A bitmap join is actually a join of a bitmap index and a non-bitmap index. A domain index. A domain index is specific to a certain type of domain. Domain indexes have specific applications of multimedia, things like maps in GIS systems, large text objects, that sort of thing. Let's see how they work. What we have here is a picture of a B-tree index. It's a very simplified picture. What I actually took was one of my tables, and I took the names from the table and I divided them up into possibly how a semi-balanced B-tree would look. As you can see, we have three levels. Effectively, the top level, which is a branch node level, the second level, which is a branch node level, and the third level, which is a leaf node level, which contains all the actual block values, or the index values in blocks. So what I did was I took my entire range from A to Z, and I found the middle of the first range of a third of A to Z, 26 characters in the alphabet, and I found an item that started with DO. So everything around DO in the first third of the letters of the alphabet would fall within this first set of branches. In other words, from 2 to JO. And there's DO starting on the second branch on the second layer. Same applies to O. We go left of O and we go right of O. Here's SI. We go left of SI with SA and right of SI all the way to TON. Effectively, what TON is the first value referencing the first item in the last block. Remember, index blocks. This is not table blocks. So the indexes, if you can see clearly here, really have the index values themselves have a row ID and the index, which is the name of the venue. What happens is I search by name, it finds the row ID, it then uses the row ID from the index to go into the table, using that logical pointer to find the exact location of the record. In theory, if you do an exact match for an exact record, you should do 1 read, 2 reads, 3 reads, and then 4 reads into the table. If you didn't have the index, you'd be doing as many reads as there are rows in the table or blocks in the table. You'd be reading a lot more records. Basically, you'd read every single record. That's the benefit of having the index. If there's 150 rows in the index table, you're theoretically reading and checking 150 rows. In this case, you're only doing 4 database reads to find this row, so it's a lot faster. However, note, it's not necessarily faster using indexes. Sometimes it can be faster with small tables to read the whole table. But that's tuning. We'll go into that on a later course. Down here I have a little note that says potential row chaining overflow. Now, practically for the amount of data I have in this table, that's extremely unlikely. However, for large tables with large indexes, you could get to the end of a block, fill the block up, and then it will row chain to a different block. That can cause performance problems later on. A bitmap index. As you can see from here, I have a table with its attached row IDs, and here I have a bitmap, which is a map of bits, ones and zeros. And here it says the state is California, and I take this first row, which is actually the first row up here, it says California, so I put a 1 in state California and a 0 in Nevada, because it's not in Nevada. If we take 1, 2, 3, 4, the fifth row and the sixth row, they're both Nevada, so we have a 1 in Nevada and a 0 in California. You can see that this index would effectively be a lot smaller than the index that was indexed on the name. It would occupy a lot less space. Imagine this being a table with 1,000,000 rows. Then you can see how much space it uses. However, bitmap indexes were originally created for data warehousing, read-only structures. Do not use them in OLTP databases because you will have severe performance problems, and they do overflow a lot, and they're not updatable. Not with any acceptable speed anyway. A function-based index. These can be useful. As you can see here, I created an index called dateOfShow on show, which is a function toChart applied to show date, which produces a value, say 2002 August. So when I do a where clause and I force it to use this index in the SQL statement, it will actually search for 2002 August as opposed to either 20th of August 2002 or the Julian value. An index organized table. We've discussed these a number of times, but here's a picture to show you table plus index placed into index organized table, and we sort the actual table data in the order of the index. A cluster, once again, is a join between multiple tables placed into a single physical object. Here's a bitmap join index. All we're doing is we're taking, for instance, the same bitmap we had earlier and a table with or without its indexes, and joining the bitmap and the non-bitmap to get a result. A domain index. Large documents, for instance in a library, lots of very big documents. Spatial geometric data. Spatial data is things like maps and objects, representations of objects, multimedia, video, sound, all that sort of stuff. There's lots of it.